All right, last week we started the discussion on introduction to filters, right? We went over the definition of filters, the types of filters depending on components used, as well as functionality of the filters, right? And then we looked at ideal characteristics of filters, right? Having the two different bands, right? Pass band and stop band, right? And then the borderline between the two bands, which what we call cutoff frequencies, right? Right here, cutoff frequencies, right? And then we looked at the ideal characteristics of each of the four different types of filters: low pass, high pass, band pass, and band reject, right? You can see for a low pass, we have the pass band first before the stop band, and you can see clearly the borderline between the two. That will be omega C, the cutoff frequencies, right? And we can see clearly because there's a sharp drop, right, between pass band and stop band, right? So you can see clearly the border, right, the cutoff frequency. And then high pass, you'll have stop band first before pass band. Again, you can see clearly the omega C that separates the two. And then band pass has two cutoff frequencies, two limits, right? Because you have two stop bands and one pass band, right? So stop band first, pass band, and then stop band, right? Again, with two cutoff frequencies. And then finally, we have the band reject, where we have, again, two cutoff frequencies, just like band pass. But now you have two pass bands instead of one, and then you have one stop band instead of two, right? So it's total opposite of band pass, right? So pass band first, and then stop band, and then pass band again, right? And then we also talked about two different ways of determining the type of filters from a circuit, right? Number one is by deriving the gain of the transfer function, and then do a test, right? Depending on the number of cutoff frequencies. If there's only one cutoff frequency, then you could perform the test at omega equals to 0 and omega equals to infinity, right? But if there are there are two cutoff frequencies, then you do the test at three frequencies, right? Omega equals to 0, omega equals to infinity, and omega equals to resonant frequency omega naught, right? That's the first method on determining the type of filter. The second way is by going straight to the circuit, right? And then do a quick circuit analysis by applying the same test on those frequencies, right? Again, depending on how many, how many cutoff frequencies you have, that would determine the number of frequencies that you need to test, right? All right. And then we look at the first filters, right? It's called low pass passive filters. So we're right now focusing on passive, no op amps. And then the very first circuit we looked at last week was series RL circuit, right? That looks like this, right? And then for series RL circuit, just like any other filter circuit, right? It is important to understand which component, or it is important for us to know how to define the output voltage, right? Which component defines the output voltage? For series RL circuit, the output voltage is defined to be across R, across the resistor, right? Then once you know how to, or where to define the output voltage, then the next thing would be deriving the transfer function right here, right? So by voltage divider, you can see that output voltage across R is equal to R over R plus j omega L times the input voltage. And from here, I can get the ratio of output voltage over input voltage, right? Which is equal to this equation right here, but then I rewrite it in this equation. Later on, I will tell you why I rewrite it this way. Okay. There's a reason why I rewrite the transfer function this way instead of that way. Okay. Okay. So let's determine the type of filter. Let's say that you don't know this is a low pass filter. How do you determine that? Again, once you get the transfer function, then you derive the gain of the transfer function, right? What is the gain of this transfer function? Well, what is the gain of R over L? That's just a constant. So that's going to be R over L. What is the gain of this denominator, which is a complex number, right? So how do you get the magnitude of a complex number? That's going to be square root of the imaginary part plus square root of the real part square plus the imaginary part square, right? That's why I get this equation right there. So now I have the equation for the gain or magnitude of the transfer function. Are there any question on this equation right here, the gain of the transfer function? If not, then again, our objective here is to be able to determine the type of filters, right? Let's say we don't know what type it is. The first way that I want you to know how to do is by again deriving the gain of the transfer function and then test it at two different frequencies, omega equals to 0, omega equals to infinity, right? Go ahead and plug in into this equation, omega equals to 0 right there. That gives you the answer of 1, right? So you can see once you plug in omega equals to 0, you get the gain of equal to 1. 1 means that V out is equal to V in. So now, right, at low frequencies, the gain is equal to 1, right, which is high, right? So in passive filters, the maximum gain you can get is 1. So that's high gain, right? At low frequencies. So at low frequencies, right? At high frequencies, represented by infinity right here, go ahead and plug in omega equals to infinity here. What do you get? You get 0, right? You get 0. So that means the output voltage is equal to 0, or the gain is equal to 0. So therefore, at high frequencies, right, the gain is, at high frequencies, the gain is equal to 0, right? So what kind of filter has high gain at low frequencies and low gain at high frequencies? That would be low pass filter, isn't it? That's one proof, or one way, I should say, to determine the type of filter from a circuit, right? Again, derive the transfer function, and then from the transfer function, you also derive the gain of the transfer function. Once you find the gain of the transfer function, then you test it at two different frequencies if there's only one cutoff frequencies, right? At omega equals to 0, omega equals to infinity. For this circuit, there is no resonant frequency, right? There's no resonant frequency because there's only one storage component. Any questions? That's the first method. The second method is to go straight to the circuit, right? Without deriving the transfer function. Go straight to the circuit and then go ahead and test the circuit at the same two frequencies, omega equals to 0 and omega equals to infinity, right? Keep in mind that the original circuit looks like this, right? You have inductor and you have the resistor right there, right? Right there. And go ahead and do omega equals to 0. What's going to happen with the inductor when omega is equal to 0? Well, when omega equals to 0, j omega L becomes 0, right? So j omega L becomes 0. 0 what? 0 ohms, right? So how do you represent 0 ohms? By a short like this, right? So now that inductor looks like a short or acts like a short, then now we know that output voltage has to be equal to the input voltage, right? If output voltage is equal to input voltage, that means the gain, what is the gain again? V out over V in has to be equal to 1, right? So now we know that at low frequencies, gain is equal to 1 or high. What about at high frequencies? Right? At high frequencies, um, omega is equal to infinity, for example, right? And then j omega L, when you plug in omega equals to infinity, that becomes infinity what? Infinity ohms, right? How do you represent infinity ohms? That's just an open circuit, right? If it's open, that means there is no current. I is equal to 0, right? If there's no current by Ohm's law, right? No current here. The out must be equal to 0, right? 0 volts, right? So therefore, the gain is equal to 0, right? So now we know that at high frequencies, right? High frequencies, the gain is equal to 0, right? So what type of filter has high frequencies at high frequencies, high gain at low frequencies, and low gain at high frequencies? That would be low pass filter, right? Any questions so far? Okay. Now, what we just did was uh, we uh, we determined the type of filters, right, from a circuit using two different methods, right? The next one is very important. So I'm going to do this slowly, and please pay attention because this next one has to do with determining cutoff frequencies, right? Now, in ideal filters, right, you can see clearly the the borderline, right, between pass band and low and then stop band, right? If it's a low pass filter, right, there's a sharp change in the gain, right, from high to low. Right? There's a sharp current right there, right? This is what defines omega C. But in real world, right, in practical filters, you're not going to get this sharp edge or sharp drop right here, right? You'll be seeing a slope, right? So you'll be seeing something like this, right? So you have a slope, right? The gain of 1 here, right? And but then instead of a sharp drop, you have a slope right here. So the filter will follow a slope, gradual slope, right? And the the amount of slope or um, yeah the what do you call it, the value of the slope, right? um, Gradual or steep, right? That would depend on the order of the filters. Right? You learned from the previous chapter in body plots that if you have 1 over s plus a, right, a pole, right, um, the number of that pole would determine the slope of the gain plot, right? If let's say n is equal to 1, right, then that would correspond to just a single pole, right, s plus a, just a single pole. And that single pole will give you a slope of minus 20 dB per decade, right? So for example, here, right, this one right here, that corresponds to minus 20 dB per decade, a very gradual change, right? How do you make it steeper? If you don't like this gradual slope, how do you make it steeper? Well, you learned from the previous chapter, right? The slope can be made steeper if you increase the number of poles. So instead of 1, make it 2, right? So double poles. If that is the case, then the slope changes from minus 20 dB per decade to minus 40 dB per decade. For example, this one right here, right? So it's steeper. If you don't like that, you want it to be even steeper than this, then go ahead and increase it to 3. If it's 3, then the slope would change to minus 60 dB per decade. So it's even steeper. Well, you get the point, right? Um, can you ever get a steep change like the ideal case? You could, but it's going to be very expensive to do so because then you have to keep increasing the number of poles, right? So in reality, that would cost you money, right? Because that means you have more and more components to put in to the filter, right? Okay. So we don't really need the sharp edge, right? In real world, it would depend on the type of requirements you have for this filter. That would determine which order of the filter you need to put, right, for the circuit. All right. But my point though is this one, right? If there is no sharp change, like the ideal, right, like the ideal filter, right? The ideal filter has a sharp change like this, right? That defines the omega c, or the cutoff frequencies. If our filter has a slope, right, like this, then how do you define cutoff frequency? So this is what's important, okay? How do you define it? If I go back to here, this is how you define it, okay? So this is very important right here. So I'm going to box this in. So cutoff frequency, how do you define cutoff frequency? By definition, at cutoff frequency, omega equals to omega c, the magnitude of the transfer function has decreased by 1 over root 2 of its maximum value, right? So here's the mathematical translation of that definition. At cutoff frequencies, the gain of the transfer function at the cutoff frequencies, right there, right? V out over V in, but when omega is equal to omega c, is going to be equal to 1 over root 2 of H max, of the maximum gain that the filter has, right? For passive filters, the maximum gain that you can get is equal to 1, right? For active, it could be anything, but for passive, the max that you can get is 1, right? So therefore, if you apply it for passive filters, then you replace this with 1, right? So therefore, if you replace this with 1, then the gain at the cutoff frequencies for passive filters would be 0.707, which is equal to 1 over root 2. That's how you define cutoff frequencies. When the gain has reached or has decreased to 0.707, that's when you can define the cutoff frequencies. So going back to this picture, right? If let's say this is the gain plot, right, of the low pass filter, you can see it has a slope right there, right? So then how do we find the cutoff frequencies? Well, maximum gain is equal to 1 right there. And then go ahead and find a gain of 0.707 right there. Let's say that's 0.707, right? And go ahead and draw a straight line for the 0.707 gain. When it intersects with the gain plot of the filter, then the frequency at which it intersects, right, is called the cutoff frequencies, right? So that's what defines a good signal from the bad signal. Anything below the cutoff frequency is considered good signals. Anything above will be bad signals. Any question on this? Make sure that this is clear, okay? This is very important to for you to understand, right? Okay. So once we understand the definition of cutoff frequencies, let's apply this definition to our current filter, right? Our current filter is low pass filter, and the gain transfer function is this equation that we derived earlier, right here, the one I boxed in right here, right? That's the gain of the transfer function. So we're going to use this to find cutoff frequencies, right? How? By setting up this equation to be equal to 1 over root 2 times H max, right? So that's what I did right here. What is it? Yeah, right there. See the gain of the transfer function, set it to equal to 1 over root 2 times H max. But H max is equal to 1, right? So that's just going to be 1 over root 2, right here. Go ahead and set it to be equal to each other. And then the omega that you get from here, right, that becomes omega c, right? And go ahead and solve for that omega c right here. Right? I solve it, and I get omega c to be equal to R over L, right? So it turns out to be for our series RL circuit for low pass filter, the cutoff frequency is R over L, right? Now, in general, right, low pass filter, transfer function for low pass filter in general, okay, follows the following format. So if I write the transfer function for low pass filter, transfer function for low pass filter in general, it would follow this format there. Okay. Now, K in this case is our gain, but for low pass filter, as I said earlier, our gain is equal to 1, right? The maximum gain is equal to 1. Yeah. H max is equal to 1. So therefore, K for our circuit is equal to 1, Our current circuit is equal to 1, right? Okay. And then omega C is our cutoff frequencies, right? So if you already know the cutoff frequencies, then you can rewrite the equation in this general format, right? Remember earlier I said, if I go back to here, when I first derived the transfer function, right? I said, okay, I derived the transfer function using voltage divider, right? And then I rewrite it this way. And I said earlier, I will tell you why I write it that way. Now you know, right? Because we just found out that omega C for our circuit is R over L. You see this equation? If I write the equation in terms of cutoff frequency, this equation becomes omega C over omega C plus j omega. See that? So it follows the general equation for low pass filter. And of course, K again is equal to 1. Right? Now, imagine if you already know this, right? If you already know that for low pass filter, it follows this equation for low pass filter. If you rewrite the transfer function, right, you derive it, and then if you rewrite it this way, right away you know the cutoff frequencies without having to derive it like we did earlier, without having to do this derivation right here, right? You set it to equal to 1 over root 2, and then you find omega C, right? So without doing this, right, at the beginning, if I already know the general form for a low pass filter to be this way, and I rewrite the transfer function to follow this format, right, then I would know right away the omega C, which is R over L. Right? That's what's nice about rewriting it in this form. Okay. Any question on this? All right. So that's the reason why I wrote the transfer function this way, because later on when we derive other filters, high pass and low pass, if you put them in this general format, then you right away know the cutoff frequencies without having to derive it again, right? Okay. Any questions? All right. So again, the cutoff frequency is R over L, and that's the general equation for low pass filter when K is equal to 1. Right. No questions? If not, let's, oh yeah, here's the difference between ideal versus practical filters, right? In ideal, you can clearly see the omega C right here, but for practical circuits, there's a slope. So you have to calculate omega C by the 0.707 gain of the gain plot to get you the actual cutoff frequency. All right. There's no question. Let's look at an example. Design a series RL filter such that the resulting filter could be used to filter out any noise above 10 Hertz and pass electric signals at or near 1 Hertz. Then compute the magnitude of V out at 1 hertz, 10 hertz, and 60 hertz to see how well the filter performs, right? And so if you read the problem statement here, right, it says design a series RL filter such that the resulting filter could be used to filter out any noise above 10 hertz, right? So any noise above 10 hertz. So block basically, right? Block any noise, block any signals above 10 hertz, and then pass electric signals at or near 1 hertz. Right? So you want to pass these signals as well as below, right? So what kind of filter would that be? That would be a low pass filter, right? Now, how do you design this? But in order to design the RL filter, right, you need to know how to size the L and the R, right? How do you get the R and the R and the L? Well, here we already know the equation for omega C, right, which is R over L, right? So if you can choose, right, if you choose omega C, the cutoff frequency, right, then from there you can get R over L, right? But how do you pick, how do you choose cutoff frequencies? Well, for sure, it's not going to be above 10 hertz, right? Because we want to block any signal at 10 hertz and above. So you don't want to pick your omega C over here, right? That's going to be the wrong omega C to choose, right? You could pick, remember you want to pass signals at 1 hertz or below, right? And then you want to block any signals above 10 hertz. So theoretically speaking, you could pick your omega C any frequency between 1 and 10, right? So any frequency between 1 and 10, that should be a good omega C, right? But for this problem, the answer I put is that for the sake of example, I choose omega C or FC in this case to be 10 hertz, to be exactly right there, right? So I'm going to pick my omega C at 10 hertz, right? Okay. And then once I know f of C, then omega C is just going to be 2 pi fc, right? That's going to be R over L, right? So if I know f of C, now I have this equation, but then you have two unknowns. So go ahead and pick one, either R or L. I'm going to pick L, right? In the previous section, somebody asked, why do I pick L first, not R first? This is a very practical question. I'm glad that he asked that question earlier in the previous section. Again, this is related to the practicality of choosing L first rather than R first. Anybody knows the reason why I pick L first rather than R? Any guess? So in real world, this is what you most likely do as well. You choose L first. The reason being, right? Again, on the paper, it doesn't matter, right? On paper, it doesn't matter which component you pick first, right? But in practice, it does matter, right? Reason being, when you select components, you'll find out that there are a lot more selections for R than for L, right? It's a lot more selection for R than for L, right? There are not as many, right, selections out there, commercially available L that you could purchase, right? So therefore, it is wise to choose L first than R, because R most likely you're going to find it, right? But L, if let's say you start from R and then you calculate L, yeah, again, most likely you will not be able to get that value of L, commercially available value for that L, again, because they're limited, right, in terms of values. But R, as you know, right, so many selections of R's you can choose from, right? So that's the major reason why I pick L first, right? Then you go through some distributors for L, look for the few values of L that are available, just pick one, And then once you pick that, and then you can calculate for R. And again, R should be, you should be able to find, um, you know, the required R from the selections, right? Is that clear? Any question on that one?
So you just picked that value out of thin air. Like there's no actual reason. Like you could have picked 200 and you could still use that. Like there's no, if we're doing this problem, we don't have to like pick within some magic range.
Yeah, for this problem, I pick 100 millihenries. Yeah, you can pick any values of L, but keep in mind, in reality or in practice, you have to pick one that is commercially available, right? Here, 100 millihenries is commercially available, right? But in terms of why I pick 100, not 200, not microhenries, that's also another practical question, right? The 100 millihenries, that's actually big, right? This is a big inductors, right? And I don't remember why I picked 100 millihenries but since I'm a power, I have a background in power engineering or in power circuits, 100 millihenries is not uncommon. So for the power circuits, you usually use millihenries type of inductors. But for electronics, right, for electronics or for communication systems, um, most likely you'll be selecting inductor that would be in microhenry range or even nanohenry range, right? It's not going to be millihenries. Again, millihenry is big, and we use this in power circuits, right? But if you have a problem like this on the final, for example, most likely I will give you the value. That way, you don't have to randomly pick any number. Okay, but I'm not too concerned about that. But my concern is, the important thing is in practical design, right? In practical design, you have to go through distributors for inductors and pick one value that is commercially available, so you can actually purchase the inductor, right? That's why you choose L first. Then the R, you can always get combination of R's, right? Okay. Does that make sense? And again, depending on the applications, that would determine how big of the inductors you need. Microhenries, nanohenries, millihenries, right? Does that answer your question? Somebody asked earlier.
Yeah, that makes sense. Thank you.
You're welcome. All right, so then here again, for the sake of examples, I chose L to be 100 millihenries, and from there, right, I know what omega C is. That's 2 pi FC. I just chose that to be 10 hertz. So then 2 pi FC would be 20 pi radian per seconds. And you plug it into here, right? And then L is already chosen. So the only unknown would be R, right? So your R value here would be 6.28, right? If this is the actual design, this is still a concern because this is not a standard, commercially available value of resistors. But at least for resistors, you can always do combination of, right? Series, parallel, and so on and so forth, right? You don't want to do that for inductors, trust me, because they're expensive, they're bulky, so you want to use only one single inductor. Yeah, a resistor, you can do all kinds of combinations, right? To get you the actual value. And they're small, right? Resistors are small. Okay. Any questions? All right, so 6.28, that's the resistor value. So once you get those two values for R and L, you could plug those in back to the transfer functions right there. Now you have a new equation for the transfer function using those values of R and L, right? And then the problem asks to evaluate performance of the filter at 1 hertz, 10 hertz, and 60 hertz, right? So 1 hertz means 2 pi times F, that's 2 pi times 1. And now you get the omega, plug it into this equation right there. And you get, if you put in 1 volt, then you can see output voltage is 0.995, right? Any reason why I use 1 volt as the input? Well, that's for convenience, right? Because eventually what I want is V out over V in, right? But imagine if I use V in equals to 1 volt, then whatever you get on the output voltage is also the same as the gain. So I don't have to actually recalculate the gain if it's 1 volt, right? Anything divided by 1 gives you the same number, right? In this case, it's actually the gain here. Right? I already brought it. So whatever output voltage you get, that's the same as the gain, right? Because again, the input is equal to 1. So it's convenience, right, to use input voltage to be equal to 1. Make sense? If you use 2 instead of 1, then you have to divide the output voltage by 2, right? That's more work, right? But if you use 1 volt, then you don't need to, right? You already know that, any number divided by 1 is equal to the same number, right? Okay, so that's the reason why I use 1 volt. Okay, so at 1 hertz, the gain is 0.995. That's good, isn't it? That's passing. At 10 hertz, that's our cutoff frequency. So we're expecting the output, the gain to be 0.707. And indeed it is, right there. Right. And then at 60 hertz, you can see the gain is 0.164. That's not good, right? Okay. We basically we block that signal. All right. The gain is very, very low. All right. So you can see that the filter performs well, right? If you pick omega C to be at 10 hertz, right? Can you make it better? Yes, you can make it better if you perhaps pick omega C in between 1 hertz and 10 hertz. Let's say, I don't know, 5 hertz or something like that, right? Then at 10 hertz, if you pick omega C to be 5 hertz, then at 10 hertz, the gain will be less than 0.707, right? 0.707 is the borderline, right? So we can make it even weaker at 10 hertz, then that would be good. Okay. Any questions? I simulated this filter right here with PSpice, and you see the gain plot, as you can see here, right? It has a slope, and at gain of 0.707, right? That's this gain right here. That's how you get the that's how you get the cutoff frequencies, right? So you can see that's 10 hertz. As expected, the cutoff frequency should be 10 hertz. Again, that happens because I put 100 millihenries and 6.28 on the filters, on the filter circuit. Any questions? And just to show you, I put in input voltage of 1 volt, right, at 0.1 hertz. So that's below 1 hertz, right? That's below 10 hertz, I should say. Omega C is equal to 10 hertz. So 0.1 is below 10 hertz, right? So it should pass very well, right? And sure enough, when I look at the output voltage, the magnitude is still 1, right? And we can see the gain is equal to 1, right? So gain is equal to 1 volt over 1 volt, right? But what happens when I put in signal of same thing, 1 volt, but at frequency of 60 hertz? Well, 60 hertz is larger than 10 hertz, right? Larger than 10 hertz. So therefore, it should block, right? Or it should weaken the signal. And sure enough, when I look at the output voltage, you can see the gain, or not the gain, the magnitude of the output signal is less than 0.2 volt, right? So therefore, the gain is less than 0.2, right? Basically, a very weak signal, right? Any question on this? All right. We are done with high pass filter. Sorry, high pass. We are done with low pass filter using series RL. Right. Now we're going to go on to low pass filter with RC circuit, right here. Now remember earlier we have RL circuit, right? RL circuit looks like this. Oops. RL circuit looks like this, right? So it's also a low pass filter, right? Now we can also have another low pass filter using capacitor instead of inductor. Out of these two, however, again, on paper, it doesn't matter which one you choose, right, for a low pass filter. But in practice, people use RC filter more than LC filter, than LR filter. Why? Why is it that RC is more commonly used than RL? Any guess? Any guess on this? Why RC is more common than RL?
Capacitors are cheaper.
Very good. Capacitor is cheaper. Capacitor is less bulkier. Capacitor takes less space than inductor. Inductor is big, right? For the same power size, power rating, for the same power rating, capacitor is much smaller, cheaper, and less bulkier than inductor. That's the main reason why, right? So again, in on paper, it doesn't matter which one, but in real world design, most likely, if you use low pass filter, you'll be using RC, right? Okay, very good. That's the answer. Okay, so again, as before, I'm going to do this faster, okay, because we're going to repeat the same thing here. It's important for us to know where to define the output voltage. For RC low pass filter, the output voltage is defined to be across C, right here, the capacitor, right? Okay, what do I do next once I know where to define the output voltage? In order for us to determine whether or not this is a low pass filter, you derive the transfer function, right? Two different methods, right? Derive the transfer function and then derive the gain of the transfer function and then test it at omega equals to 0 and omega equals to infinity, right? Let's do that quickly. There's the transfer function right there, right? And then I rewrite it this way. And from the previous discussion, can you now know the answer why I rewrite it this way? Anybody? We talked about it earlier. In general, the transfer function of a low pass filters follows this equation right here. So why is it that I rewrite it this way? Come on. Uh-oh. Why? Because if you rewrite it this way, you don't need to derive the cutoff frequency anymore, right? Remember, in order to derive the cutoff frequency, you have to do this derivation, right? You get the gain of the transfer function and set it to be equal to 1 over root 2 times H max, right? Which I'm doing also next shortly. But right, we don't need to do this derivation if we rewrite the transfer function this way. Because right away, if I compare the general form of the transfer function for low pass filter with this transfer function right here, right away, I know what omega c is right there, right? So I know omega c for this circuit is 1 over RC. That's the advantage of, or the benefit of rewriting it that way, right? Okay. All right. So, but again, I'm going to do this anyways later on. But what do I do with this transfer function? You get the gain of the transfer function, right? Which again, I'm going to use to find cutoff frequency later on, even though we already know, right, what it is from this transfer function. Once you get the gain of the transfer function and you test it with two frequencies, right? Omega equals to 0 and omega equals to infinity, right? And omega equals to 0 from the transfer function, right? You go ahead and plug in equals to 0, you get 1, right? So high gain at low frequencies. And then at high frequencies, you can see the gain is equal to 0. So that's low gain at high frequencies, right? What type of filter has high gain at low frequencies, low gain at high frequencies? That's low pass filter, right? Any question on this? And then what do I do with this? or not what do I do, but what is next? What is the second method? You go straight to the circuit, right? Right, just like this, right? When omega is equal to 0, remember we have R and C, right? When omega equals to 0, capacitor acts like an open, right? Becomes infinity, right? If it's open, that means there's no current here, right? So therefore, the entire voltage across R will be 0, right? Like KVL, if voltage across R is 0, that means voltage across the capacitor must be equal to V in, right? So V out is equal to V in, meaning gain is equal to 1. Again, at low frequencies, high gain at 1. At high frequencies, right, the capacitor acts like a short, right? 1 over j omega c. Go ahead and plug in omega equals to infinity. That gives you 0 ohms, right? How do you represent 0 ohms? A short, right? What is the voltage across a short? That's 0 volt, isn't it? Right? So therefore, at high frequencies, the gain is 0. And so at low frequencies, the gain is high. At low frequency, the gain is 0. So therefore, we have low pass filter. All right. Any question on this? What's next? Well, cutoff frequencies, right? Applying the definition of cutoff frequencies, which is what? 1 over square root of 2 times H max, right, of the gain. That's equal to the gain at omega c, like that, right? So that's what I did right here. Our H max is equal to 1 for passive, right? So therefore, I set it to equal to the gain of the transfer function. We already know from the transfer function earlier that our cutoff frequency is 1 over RC, but this is just mathematical proof that it is. Once you set this equation, then you can get omega c to be equal to 1 over RC as expected, right, from the previous transfer function, right? Any question on this? No? So now we are done with low pass filters, passive filters. The next one is high pass, passive filters. We just did RC, right? That looks like this, right? And this RC circuit is a low pass filter if I define the output voltage to be across V out, sorry, across V out, across C, right? This is important because if you somehow made a mistake, right, instead of defining the voltage, output voltage across C, you put it across R, right there. Then you will not have low pass filters. What you have is high pass filters, right, which is right here. See this? Right. So it's a high pass filter. How do I know this? Well, if you derive the transfer function, right here, right, just like I did before, right, and then I rewrite it this way from the transfer function. I rewrite it this way. Any reason why? Now you should know why I rewrite it this way. For low pass filter, the general transfer function follows k omega c plus j omega. For high pass filter, it follows, I'm almost done here, k j omega plus omega c. If you rewrite the transfer function this way, right away you know the omega c. Check this out. Go ahead and compare the two. Right. So if I rewrite the transfer function this way to follow that format, I can right away tell that for a high pass RC filter, omega c turns out to be 1 over RC again, just like the low pass filter. And we'll continue next time, okay?